All right, welcome to section 3. So yesterday we talked about proportions, setting up proportions, and solving. Today we're talking about similar polygons. So today we will be heading back into shapes and polygons. We're first going to identify similar polygons. What do I mean by similar? How would we define that? And then we're going to use what we know to solve a couple different applications. In this section, you'll be able to start making a little bit more sense of some of those kite project instructions. So some of the requirements for the blueprint are going to come from this lesson. So make sure that we are good to go with what we're talking about in section 7.3 before we get too far ahead with our blueprint. So here is your definition. Similar figures have the same shape, but not the same size. The little symbol that we use for is similar to, it's just a little squiggle. I'm just going to use that. So for example, I have these lovely trapezoids down here. I'm going to say that ABCD is similar to GHIJ. When we have similar polygons, there's something special about their angles. So I am going to mark up some of these angles using some different colors here. And then we are going to write some statements based on what we are seeing. So within a similar polygon, I should have corresponding angles that are congruent. So I can say that angle A is congruent to angle G. I can say that angle B is congruent to angle H. I can say angle C, congruent to angle, whoops, forgot the angles. And angle D is congruent to angle J. So corresponding angles, and you guys have heard that word corresponding a lot, corresponding angles in similar polygons are congruent. But the sides are not congruent. So you guys have dealt a lot with congruent triangles, different types of congruent figures where all the sides, you had pairs of corresponding, sides and angles that are all congruent. In the world of similarity, it's a little bit different. So corresponding angles are congruent, but corresponding sides are proportional. So that is why we needed to talk about proportions before getting into similar figures. So what I could say here is that side AB, this side right here, over side GH is going to have the same proportion as my next pair of corresponding sides, BC and HI. It's going to have the same proportion as CD and IJ. It's going to have the same proportion as AD and GJ. And hopefully you can see order of letters matters here, right? A corresponds with G, D corresponds with J, B with H, C with I. All right. So this is the different thing. This is called an extended ratio. We talked about these earlier on this week, extended ratio or extended proportion. We're going to use these. Oh, I spelled proportion wrong. How embarrassing. Proportion. We talked about these earlier on. We're going to use them to help us solve for some missing pieces here. But the main idea with similar polygons is corresponding angles are congruent, corresponding sides are proportional. And instead of using a little congruency symbol, we are using our similarity symbol, just the top of the congruency symbol. Let's keep going with this. Let's do an example. In this figure, we see two similar shapes. Here is what we call a similarity statement. Similarity statement. You guys have dealt with congruency statements. There's going to be a lot of things that are kind of the same, but a little bit different with similarity. Order of letters does matter. So what are the pairs of congruent angles? You could either use the diagram or you can use the similarity statement. Angle M is going to be congruent with angle S. So this fella and that fella. Angle N is congruent with angle R. This guy over here with this angle up there. And lastly, angle P is congruent to angle T. 1, 2, 3, 1, 2, 3. All right, so Sometimes the similarity statement helps. We saw that with congruency too, because sometimes the orientation might just look a little different. It might be a little tricky to figure out which angle exactly corresponds with which. Just use the order of the letters to help you out there. What is the extended ratio of sides? So I'm going to start with my first two letters over here, MN. Oops, MN. What should that be over based on that previous slide? Hopefully you are saying MN should be over SR. The ratio of those two sides is going to be equal to the ratio of NP, side NP, our longest side over here, with the longest side of the other triangle, RT. And then lastly, MP should be over ST. So this proportion is the same for all corresponding sides. I'm going to actually write that down here. This proportion, again, this is called an extended ratio. This proportion is the same for all pairs of corresponding sides. All right, let's keep going. Okay, here's something that you all are going to have to use on your kites. A scale factor. A scale factor is the ratio of corresponding linear measurements, or maybe we could say sides, of two similar figures. So for instance, let's say I have a pair of corresponding sides. I have BC. Well, actually, I'm not going to put a line over that because I'm talking about distances. BC, 20 inches, and YZ, 8 inches. All right. There's a pair of corresponding sides. Maybe I have, a parallelogram ABCD and another parallelogram WXYZ. Okay. I shouldn't have put them in that order, but BC and YZ, those are corresponding sides. Okay. To find my scale factor, I just need to find the ratio of BC over YZ. So 20 over 8, and it's inches and inches, of course, but those would cancel. This would all simplify to 5 over 2. So this right here, that 5 over 2, that is our scale factor, or sometimes we just call it our SF. So what you all are going to have to do with your kite projects is figure out, what is your scale factor for your blueprint and your actual kite. If you're dealing with corresponding sides, what is the ratio between corresponding sides? On your kite, you'll have two sides that are the same length and another pair of sides the same length. I don't know, let's say that one of those sides is, I'm going to use a preposterous example here. Let's say that one side of your kite is 20 feet. On your blueprint, well, what is that going to be? Is that going to be 2 inches? Is that going to be 2 centimeters? Is that going to be 1 centimeter? Like, what is that going to be? So you're going to have to consider what actually is your scale factor for your kites. Let's keep going. Are these polygons similar? If they are, write a similarity statement, so with that similarity symbol, and then give the scale factor. So let's see if these things are. So first we're going to identify congruent angles. So over here I can see that angle K is congruent with angle U. I see that angle J is congruent with angle T. Angle M is congruent with angle W, and angle L is congruent with angle V. This is looking good. Okay, I have 4 pairs of congruent corresponding angles. So far so good. It's looking like they might be similar. Let's check if the extended ratio would work. So what we're going to do is we're going to compare ratio of sides. So first step was identify congruent angles. Second is compare ratios of sides. So I need a pair of corresponding sides. Well, let's start with maybe MJ and WT. Those would be a pair of corresponding sides. So if I look at JM over TW, that would give me 6 over 6. If I simplify that, it's just going to be a 1-to-1 ratio. Okay, again, I am going to put 1 over 1 because when we're dealing with ratios, I want 2 numbers, right? It's a 1-to-1 ratio here. All right, let's look at another pair of corresponding sides. We have JK. And we have TU, that would be 12 over 6. That would be a 2-to-1 ratio. Okay, already this is not looking good. I'm going to put the rest of these just to, double check ourselves here. KL to UV, that's giving me 24 to 16. What would that simplify to? Well, they're both divisible by 8, so that would give me 3 over 2, a 3 to 2 ratio. And then lastly, I have LM and VW. That would be 24 over 14. Most I can divide those by is 2, so 12 to 7. So these are our different ratios. Man, none of these are the same, okay? So because these are not equal, that means the polygons are not similar. Aren't similar. So I cannot write a similarity statement, and I cannot write a scale factor. This is a classic case of don't trust the diagram. Do not trust that diagram. At first glance, it looks like these might work, right? But then when we actually set up the ratios, we can see, oh, clearly these corresponding sides do not have the same ratio, all right? So always go based on the numbers over the diagram. Let us move on. What about these guys? Are these polygons similar? Again, we're going to start with step 1, identify corresponding angles. So I see that angle A is congruent with angle D. I see that angle B is congruent with, 3 arcs, angle E. And then angle C must be congruent then with angle F. Okay, so far so good. Nice. I have 3 pairs of congruent corresponding angles. Let's check our sides. I'll start with side AB. What would my corresponding side be in the other diagram? So AB would correspond with DE, okay? So that's going to be 12 to 15. I can simplify that a bit. That'll be 4 to 5. Let's do BC. BC would be corresponding with which one? All right, we're looking at EF. So I have 16 over 20. How would that simplify? Well, I could divide both by 4, so 4 over 5. And then lastly, I'm looking at AC over DF. That'd be 8 over 10, which would also simplify to 4 over 5. So all of these are equal because I have equal ratios. Then yes, I can write a similarity statement. I may write a similarity statement. Triangle ABC is congruent to triangle DEF. And I can use that little symbol. Before I just had to say like polygon, blah, 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 or don't even say polygon, just list letters. We're dealing with triangles, so use that triangle symbol. And the scale factor for this would be 4 to 5, or 4 over 5. All right, y'all are doing great. Let's keep moving along with this. We have another example. ABCD, so this larger diagram out here, ABCD is similar to this smaller guy inside here, EFGD. Those two are similar. What is the value of X? And then what about Y? So what ideas do we have to solve this? Well, I see that X is right here. That's side FG. FG corresponds to which side? Okay, BC. So I want to use the similarity statement. So this guy right here, use the similarity statement to write a proportion. We said that FG is corresponding with BC. And I can set that equal to any other pair of corresponding sides. Let's be smart here. Let's set this equal to a pair of sides that I already know. So for instance, ED, that corresponds with AD. And I've already been given some numbers for those. Like I see that ED equals 6, AD equals 9. So let's go ahead and replace each of these sides. FG is X, BC is 7.5, ED is 6, AD is 9. I'm going to go ahead and cross multiply here. So 9 times 6 equals 6 times 7.5. It's going to give me 9. Oh, sorry, not 9 times 6. 9 times X equals 6 times 7.5. 6.7.5. What would that end up giving us? Cool. To give us 45. I'm going to divide both sides by 9. I am left with X equals 5. All right, so that's our first answer. And again, you can always kind of check yourself by saying, hey, 5 over 7.5, what does that actually simplify to? Well, if I divide both of those by, 2.5, that would give me 2.3, or 2 over 3. 6 over 9, what does that simplify to? 2 over 3, boom. Okay, that's just kind of your nice little check. Did we get the right answer? 5 is correct. How would you guys find Y? Honestly, do a very similar thing over here. I know that EF corresponds with AB, so I'm going to say y over 5 equals, let's just reuse the other sides, 6 over 9. Solve it out with your cross products. 9y equals 5 times 6, so 9y equals 30. Divide both sides by 9. It's going to give me y equals, okay, 30 divided by 9, that's either going to give us 10 over 3 if we want the exact answer, or 3.3. So that is what we were looking for over there. That is your answer. Or again, 3.3 would work too. Okay, let's try a word problem. Your class is making a rectangular poster for a rally. Actually, we might have a pep rally coming up soon, so that's actually kind of funny. The poster's design is 6 inches in width by 10 inches in length. The space allowed for the poster is 4 feet in width by 8 feet in length. Okay, so the poster's design is this. Again, kite application here, and for the next one too. You guys are creating a design, and the next week the design is going to come to life as a physical model in the real world, okay? But we need to be kind of careful about this. So the poster's design is 6 by 10. The space allowed for the poster is this over here. What are the dimensions of the largest poster that will fit in this space? So we are not going to be able to have a 4 by 8 foot poster. That's not going to happen, but that's the maximum dimensions that I possibly could have, okay? So let's kind of think about this. How could we figure this out? First of all, I'm dealing with a couple different units over here. So I'm going to start with my width. Start with width. All right. So the poster design is 6 inches in width. And I know that my maximum width in the real world would be 4 feet. I want to get those in the same dimension. So what is 4 feet in inches? 4 feet, hopefully you guys know this, 48 inches, right? 12 inches in a foot, 4 times 12, 48. So how many of these posters could I kind of fit in there? How many 6 inches fits in 8 inches? What is 48 inches divided by 6 inches? 8. Okay, so it seems like maybe I could scale my poster up by 8, but let's check our length and check those dimensions over there. I know that I'm dealing with a design of 10 inches, and I know that I maximum could have a poster that's 8 feet. So what is 8 feet in inches? 8 times 12. It's going to give us 96. How many 10 inches can fit in 96 inches? So what's 96 inches divided by 10 inches? Well, that's going to give us 9.6. Okay, so I could either scale this up by 8, or I could scale this up by 9.6, which makes sense logically. I'm going to have to choose the smaller number over here. So we're going to choose the smaller number, because if I went any bigger than 8, well, then I wouldn't have enough width for it, right? The length would be okay, but the width would be too much. So the design can be, I'll write this down here. The design can be enlarged eight times. That is our answer here. All right. So you'll see other problems, excuse me, pop up like this. The main thing to do here is figure out, okay, how could I scale up my width? How could I scale up my length? And then choose the smaller number. That's going to kind of give you the max that you could actually go, the highest you could actually go. Folks, we have one more problem left. Let's get into example 5. Again, another good kite application over here. So here they're talking about literally a scale drawing. You guys are going to be doing a scale drawing with your blueprint of New York City's Empire State Building using the scale 1 inch corresponds with 250 feet. So you guys are going to have to figure out, what is my scale? 1 inch on the paper corresponds with what in the real world? If the building is 1,250 feet tall, how tall should you make the building in your scale drawing? So guys, how would you set up a proportion here? This is honestly kind of similar to yesterday, really. Well, I need to figure out how many inches is going to correspond with 1,250 feet. So I'm going to say 1 over 250 equals x over 1,250. Let's go ahead and cross multiply. 1 times 1,250 is 1,250 equals 250x. Divide. We are getting that x should equal 5 inches. All right. So as you're gathering in your groups and starting to think about your blueprint and your kite project, think about, how big do I want this thing to actually be in the real world? And think reasonably. Like we talked about this a little bit earlier this week, you will not be able to build a 10-foot kite unless you're bringing in the supplies. I have had some very large kites, but also be reasonable. You have one part of a class period to physically construct this thing. Okay. So keep in mind, what kind of dimensions would make sense in the real world, and then how could you use something like this problem to kind of figure out, okay, well, what's my skill going to be? What should actually be shown on my blueprint? And I'm going to be taking rulers and yardsticks and measuring things and making sure that they're lining up. So I really want you guys to put work into making this detailed, making this careful, making this neat. All right. And I know you guys can do it. It'll be awesome. And hopefully we'll get some flying kites. Folks, at this point, move on to the rest of your sub-plans. You'll have some homework. You might have some other things that I added in to the plan. Thanks for watching.